We're going to get started in a couple minutes here. The bell being here is not as useful because I know when we're starting. I asked for a bottle of water and they brought these, and I was like, sometimes I want like an American-style disposable bottle.
The camera frame currently goes to about center stage. So try and.
So don't walk beyond there. Okay. He's good. Yeah. Yes.
About this line.
About that line? Okay.
Yeah.
I'll try to just stay still. I'm used to pacing.
So you're going to hand me a mic that's hot?
I'll hand you this mic. Yeah, it's hot.
No, I'm not going to give it to John.
That's right. John's got his own mic.
John is in. John ready for.
Are we good?
Yeah.
All right, everybody, we're going to get started in about 60 seconds here. So please take your seats, wrap up sentences and conversations. That was fast. See how long the silence can drag out. All right. Good morning, everybody. Welcome to Copenhagen. Welcome to day one of PLDI after 2 phenomenal days of workshops and tutorials. And welcome to our first keynote session. Before we get that part of the process started, I wanted to say a couple of things. One, for those of you who don't know me, I'm Milind Kulkarni. I'm the general chair of PLDI. So all credit for anything that goes well goes to our amazing organizing committee and staff and AV chairs and things like that. Things that are not going well, come bug me. Don't bug them. So welcome to Copenhagen. I think we've rolled out a phenomenal set of events for you and also some phenomenal weather. So I hope you guys enjoy your time here. This is only my second time in Copenhagen, and it gets better every time. I want to give a very special thanks to our many, many sponsors. You're going to see their names on the wall out behind the registration desk. We have a ton of sponsors, which we'll talk a little bit more about at the business meeting. But I especially want to thank our platinum sponsors, AWS, Apple, Huawei, and the University of Copenhagen. So thank you to them. It is because of their generosity that we're able to do so many of the things that we're doing this week. If you are interested in participating in the various virtual events of the program, including if you are a virtual attendee, Q&As for all of that will be handled through our Discord. You should have all received an email asking you to sign up, but in case you didn't, this is our Discord, and so please sign up. There's going to be information, opportunities to connect with each other, organize dinners, things like that. I'll let you grab that QR code. Okay. A couple of schedule notes. First of all, and this is important because it's a little bit confusing, lunch is actually going to be in 2 locations, Wednesday, Thursday, and Friday. Lunches will be both on this floor in the ballrooms that are across the floor on the other side here, but they will also be down in the Fellini restaurant. So those of you that were here Monday and Tuesday for workshops and tutorials, that's where we had lunch then. If you're getting breakfast, that's where you're getting breakfast. Lunch is in both locations. There's too many of us to all fit in one location. There is food on both floors, so don't think that you have to grab your food up here and walk downstairs or vice versa. Just go to either floor and grab food. There are also 3 special lunches that we are organizing, one each day. So on today, Wednesday, there's the SIGPlan mentoring lunch if you're part of the SIGPlan long-term mentoring program or are interested in joining it. So that will be up here on the first floor. On Thursday, we're going to have our LGBTQIA lunch. That is going to be in a semi-private room in the Oslo part of the floor up here on Thursday. It is open to anybody that feels that they want to participate. So if you don't feel like you have to register for it, if you are finding out about it for the first time now and would like to attend, please do. Similarly, we have a URM lunch also in Oslo on Friday. So those are kind of our special lunches. Special in the sense that it's a specific group, not special food. Same food for everybody. So a couple of other scheduling notes. There's a reception and student research competition poster session this evening, right after the last session up here on this floor. So please attend that. If you are an SRC poster presenter, make sure you talk to Alexa and Aurel about getting everything set up and how that's going to work. We are going to do our business meeting and awards banquet on Thursday. We're going to announce all of the distinguished paper, distinguished artifact, and SIGPlan awards at that dinner on Thursday. Everybody who is registered is invited to that dinner. Don't feel that you had to purchase a special ticket. So please attend that and find out who won all the various awards this year, both from PLDI and SIGPlan. Couple last minute things. Thanks to our PLMW folks and our social folks. We're doing a little bit of a networking game. So if you are interested, there's going to be SIGPlan bingo cards available this afternoon. It's an opportunity to get to know some of your fellow conference attendees, finding out where people are from, how long they've been in the community, things like that. And the student who completes the most bingos by the end of the afternoon break tomorrow, we'll announce them at the awards banquet. So, feel free to do that. There will be, you don't have to take pictures of the cards. We'll have them handed out this afternoon. Okay, some important notes here. We are an ACM conference, which means that we do subscribe to ACM's policies against harassment. So we expect everybody in this room, everybody that's participating in any of the events this week, to abide by this policy. Please exercise consideration and respect in your speech and actions, refrain from demeaning, discriminatory, or harassing behavior and speech, and please alert community leaders if you notice a dangerous situation or someone in distress or violations of this policy. We take it very seriously as members of the ACM, so this is important. If you would like more details about the policy, there's a link here. Also, speaking of people that are in charge that you can alert to issues that you might be experiencing or you might be noticing, SIGPlan Cares is a SIGPlan-wide organization to help folks that are experiencing some of these issues. It's a community support group. It was established a couple of years ago, and they can provide information. They can chat with you if you just need a friendly ear, and to basically to support people that have experienced or have witnessed unacceptable behavior. In particular, there's a number of people that are part of the SIGPlan Cares organization. I've highlighted two people who are in attendance at the conference, Sokyung Roo and Steve Blackburn. So please do find them if you feel that you need to avail yourself of their services. And with that, I would like to turn the mic over to our program chair, John Regehr, who is going to introduce our first keynote speaker.
Good morning. Super excited to kick off our technical program. So each of Wednesday, Thursday, and Friday we'll have a keynote. I'm really excited to kick this off with Jonathan Reagan Kelly. He's going to be our first speaker today. Jonathan is an associate professor in the ECS department at the Massachusetts Institute of Technology in the USA. He does a really broad variety of work. His work spans systems, languages, compilers, graphics, and more. And he's probably best known for being a co-creator of the Halide programming language. And take it away, Jonathan.
Thanks. Water doesn't want to stay up. All right. So hi. Thanks for having me and thanks for coming. I'm really honored and excited for the opportunity to be here. And thinking about what I wanted to talk about, John was suggesting talking something about the future of high-performance hardware and what it might mean for programming systems. So today I want to talk about hardware and our relationship to it as programmers and programming system designers. So computer hardware is amazing today. One of my students is into LLMs, and in a given week he trains several billion parameter models on tens of billions of tokens of internet text. And one of these training runs requires about 180 exaflops of computation, but only takes him a day to run on 8 GPUs. Now this is a Cray 1. It was the fastest and most expensive computer in the world 50 years ago, and the machine that popularized the term supercomputer because it was so insanely ambitious and powerful at the time. But even if it had enough memory and perfect code that used all 160 megaflops of its theoretical peak performance, it would take 35,000 years to run the same computation, 13 million times longer than a single grad student with a couple GPUs today. And people worry about power in modern data centers. But in addition to being insanely expensive, a single Cray 1 burned 115 kilowatts, or around a kilowatt per megaflop, or about 1 billion times less energy efficient than a cluster of H100s. Now, to the younger people in the room, 50 years may sound basically infinite. Of course we can have arbitrarily large change in that time, but for comparison, this is a car from 1975. It's a bit less safe, a little less fuel efficient than a modern car, but it carries the same number of people at basically the same speed on the same roads. And this is a passenger jet from 1975. It looks probably just like the Boeing 737 you flew on your way here, because it is a 737, which came out almost 10 years before that in 1967. So this one is repainted, but it's an original Model 200. So this could have been bought in 1975. And again, it's the same speed, but we've improved fuel efficiency by maybe 2x. The point is, in the arc of human development, 50 years actually isn't that long. But the fastest computer hardware for numerical computation is improved by a factor of 1 billion. Even my fanless laptop and phone each have tens of teraflops of compute spread over CPUs, GPUs, and other accelerators on a single tiny chip. So this is an amazing gift. But now what happens when we actually try to use it? So let's say I want to multiply some matrices. That's a classic problem used all over the place. The hardware should be good at it. And I know it's at the core of modern ML models too, so it's trendy. So to start out, maybe we could use many people's favorite, probably my favorite high productivity programming language, Python. And we can write matrix multiply from scratch in just a couple lines of Python. This is easy. Now, of course, I know there are optimized library functions to do this specific operation, but as programming system designers, I don't think we should find that alone to be a very satisfying answer. People should be able to write new programs themselves. We program to solve new problems that aren't necessarily in a library. And even for MatMul, somebody has to write it. OK, so if we run this code on my laptop with the latest Python, we get about 10 megaflops. So that's actually slower than the Cray 1, or about 0.00005%. I think I got the number of zeros right. Many orders of magnitude below the combined theoretical peak performance of all the potentially relevant hardware on my laptop's M2 chip. Now, we all know that Python's slow, but I want to put in perspective just how slow this really is. Now, of course we can do better. Python's not even compiled. So what about JavaScript, which has some of the most advanced JITs around today? So here we get about 500 megaflops. So it's 50 times faster than the Python for this type numeric loop. But that's still just 0.0025% of the hardware's potential. What about dropping down to C, switching to explicitly using 32-bit floats, making sure we're using the newest compiler and all the right optimization flags? So this is twice as fast again, so 100 times faster than Python, or now up to 0.005% of what our machine could do. So surely we can do better than this. Well, if we think for a bit about caches, we read through the generated assembly, we can realize that this kind of canonical loop order I'm using actually has poor spatial locality. And it only accumulates to a single entry of C across this whole innermost loop, which prevents easy auto-vectorization. So it turns out just by swapping the two inner loops, we can do about 20x better, jumping all the way to 20 gigaflops, or a whole 1,000th of the peak performance of our machine. Rewriting and tuning everything over several hours with multiple levels of cache blocking for locality making sure the inner loop is really well vectorized, reading the assembly coming out of the compiler and tweaking it. I was able to push this up to about 40 gigaflops on a single core with a moderate amount of effort. And then parallelizing and further optimizing for multi-core gives us 5x more on 4 performance plus 4 efficiency cores here. Now, I want to be clear, this 200 gigaflops is around 40% of the theoretical peak vector performance on just the CPUs. So it's not that bad for an evening of hacking. But it's still just 1% of the chip's total ability. And even just on the CPUs, we can go almost 8 times faster by dropping down to 16-bit float and rewriting all the code to target their matrix units instead. And in this case, spending expert months tuning and optimizing that to the limit. So at this point, we're finally into the teraflops. But we've still only even turned on a relatively small fraction of the whole chip. We can target the GPU by starting from scratch and writing hundreds to thousands of lines of metal compute shader code. It's a language based on C, but with a completely different programming model. This laptop has a relatively modest GPU, so we get just about double the performance again, or around up to 15% of the hardware peak. And finally, this chip has a 16-core NPU, which Apple calls the neural engine. This only works on fixed point data, so we have to quantize our problem to int16. But once we do that, we get a whopping 16 teraops per second. And this is the single biggest chunk of total capacity in the chip. While its interface is proprietary, we know that most accelerators like this are actually a bunch of embedded processors driving matrix multiply units, which is an idea we'll come back to later. So while we can't code to this directly ourselves, someone had to program and optimize the embedded kernels that actually get this performance. All right. Putting that all together, where does this actually leave us? So we know it's possible to get teraflops on the CPU or tens of teraflops on the machine as a whole. 6 orders of magnitude faster than the simple program that we started with, and 4 orders of magnitude above even a basic C program. But it requires enormous effort and deep specialization of the code to this one machine. And if we want to scale even further and exploit the petaflop or more that we can get on a GPU like an H100, we need completely different hyper-optimized code all over again. So hardware is amazing, but this gap between reasonable efforts, writing clean, modular, portable code, and the very best performance achievable with unbounded effort is enormous. And it's a big problem if we actually want to use this bounty that the hardware gods have given us. So I'd argue that 90% of NVIDIA's market cap and the insane margins that they're able to charge all of us are because they're the only company that's consistently able to ship enough of these hyper-optimized kernels for each new generation of hardware to actually deliver reasonable peak performance on all the ML models that everyone wants to run. But why does this gap exist? I think a key factor is that as much as hardware has changed, the way we build everyday software largely hasn't kept up. Now that might sound provocative. So, PLDI's roots also date back more than 50 years. And this community has been doing lots of great work to improve programming the whole time. And I'd obviously much rather use the tools of today than 1975. But a bit like the modern car or airplane, I think the core of how we program would still be pretty familiar to someone from 50 years ago. Concretely, by 1975, we already had Unix, C, modern virtual memory, decades of work on optimizing compilers. In the functional world, we had ML and type inference. We even had Smalltalk and the first graphical user interfaces running on networked personal computers if you were lucky enough to be at Park. So if you showed the code of a modern web app to a young Alan Kay, or a modern matrix multiply kernel to Seymour Cray, I think they'd find them pretty familiar. And the most significant thing, I think, is that things like a sequential scalar model of primitive computation, a uniform global heap memory, and building abstraction through opaque subroutine calls and pointer indirection have always been the core abstractions of mainstream programming models. And this made lots of sense on a mini computer from the 70s like a PDP-11. But these programming models have diverged more and more from the realities of hardware since then. To the point where we just saw that reasonable C code, even after optimization and a heroic vectorizing compiler, may still only get 1/1000th the performance of even a small computer like my laptop. Now, traditional CPU architecture is all about indulging this fantasy by providing the illusion of a machine that does one simple thing at a time, one after another. So basic scalar arithmetic and logic, conditional branches, or loading or storing individual values in a uniform global memory. Mainstream CPUs, even ARM, still have instruction sets dating back to this time in the 70s and 80s. But there's been a divergence in hardware architecture between those that try to go as fast as possible given only this simple archaic model, big out-of-order CPUs designed to run web browsers and transactional databases, and architectures that instead promise to be way faster, but only if you're willing to dramatically change your programs. In our dominant programming models, the core of things like C, Python, JavaScript, or even I'd argue Rust, OCaml, and Haskell still mostly conceive of computers as really fast PDP-11s. And what I want to convince you today is that if we want to unlock the potential of the fastest and most energy-efficient hardware that humanity can build, we need to rethink our programming systems. And to do that, we first need to better understand the hardware and the reasons why it wound up this way. Because I think most of the reasons are fundamental, not accidental. So that's where I want to spend a chunk of time next. Now, a quick disclaimer, I'm not a computer architect or hardware designer. I'm a graphics and programming systems person. But what I'm going to share are some ways that I've found it useful to think about the fundamental forces driving hardware performance. And I owe a huge debt, especially to Mark Horowitz, Bill Daly, and Krista Asanovich, who helped me learn most of what I know about hardware. And the way I'm going to present some key parts is heavily inspired by Keyvan Fatalian. So if they get credit for good ideas, all the mistakes are on me. Now, with that, what actually makes hardware fast? Well, the classic PDP-11 view is basically executing a sequential stream of instructions in as little time as possible. And how can we do that? So let's say this is my processor, and this is running this program. For each instruction, it has to read it, figure out what to do, and then do it. So for each instruction, it has to fetch it from memory, decode its meaning and configure its execution units to do what was asked, fetch its operands, actually execute the operation on them, and then write back the result. So it's basically an interpreter for the instruction set, but built in hardware. Now looking inside the actual hardware, we have logic responsible for controlling the whole process, fetching and decoding instructions, a unit to execute the actual operations, like multiplying two values here, and we have storage for program state, the registers holding actual values. So a simple processor handles one instruction every clock cycle. Now how can we make that go faster? Well, first we can just crank up the clock speed. So we still do one instruction per cycle, but we do more cycles per second. There's several ways we can do that, but the catch is that all of them come at a big cost to efficiency, especially power efficiency. And this is why clock speeds haven't been growing nearly as fast in recent years. Fortunately, another thing we can do is exploit parallelism. So if we look back at the dependencies between instructions in our program, we can see that not every instruction depends on all of the ones before it. So we should be able to execute them in parallel. So some can be trivially executed in parallel, while others could be if we were clever enough to also execute them out of program order without violating the sequential semantics. So concretely in hardware, we can make our processor bigger, lay down multiple parallel execution units along with significantly more control logic to control them all. So its job is going to be to dynamically track dependencies and look for opportunities to execute in parallel. And its key responsibility when doing that is going to be to maintain the illusion that we are only ever running one instruction at a time in program order even if we actually execute many in parallel and totally out of order. And it's doing all this dynamically in hardware while running the program. So we're always paying a cost for this while the hardware runs. Another key problem is how to avoid stalls. So out-of-order execution helps with this, but things like branches are still a fundamental obstacle since we don't know which way they go until they're actually evaluated. And memory is a problem because the latencies there are especially large. So the common trick here is to speculate, to keep ourselves busy doing things we think might be useful but aren't sure yet, so we're ready when we need them. So we can make our processor bigger again and add branch predictors that guess which way a branch will go, as well as more complex logic to undo the speculative execution in case we were wrong. We can add caches to store recently used data nearby, guessing that it might be used again. And even memory prefetchers that guess what values not yet in the cache might be useful in the near future and load them speculatively. So adding these techniques bit by bit made a lot of sense when a practically sized computer could only fit one processor. But today, even the largest, most complex out-of-order core is only a single-digit number of square millimeters of silicon. So you can fit literally hundreds on a single chip. At the same time, it's easy to see that we most need performance when processing lots of stuff. So it's the fact that we have billions and billions of pixels, database records, and neural net activations that tends to make us care about getting performance. So while I know not everything is easy to parallelize, I'd argue that most of the apps where we're really desperate for more performance actually have lots of data parallelism by nature. So these two things point toward a different view of performance. So we don't really care about the time to process each individual item. We care about the overall rate at which we can process lots of them. So I call this a throughput-oriented view of performance. And this reframing helps explain all the ways that high-performance computing has changed in the past couple decades. So fundamentally, three things drive throughput. So we have the amount and complexity of work that we want to do, the amount of resources we can bring to bear on it. In hardware, above all, that means things like silicon chip area and energy. And the third factor is the efficiency with which we apply all those resources, or how much we apply to useful work on the actual task versus all the meta work around it and what we waste doing nothing at all. And these first two are usually constraints set by the application context. So given a task and resource budget, we want to spend as much of our resources as possible doing useful work towards the task. So stepping back to our processor, if we have more silicon, we can either spend it beefing up all the stuff in our one core to run one sequential thread of instructions faster, or we can just throw down twice as many cores. So in the throughput-oriented view, I can double performance with twice the cores. So if I spend my resources on anything less efficient than that, I'm wasting my time building a slower machine than I could have had with more cores. So thinking about what we did to make our conventional processor faster, the problem with all of these things is that they have very sublinear returns. So they fairly quickly hit the point where doubling the resources you throw at them, you might only hope to get like 10% improvement in performance. And if we actually look at high-performance CPUs over time, we can see this quite plainly. So here I'm going to plot the estimated size of a processor core normalized across process generations on the x-axis. So this is the amount of hardware resources being used to make one core. And on the y-axis, we have the performance per clock. So this is how much useful work that hardware does every clock cycle. So this first data point is one core from Intel's Core 2 Duo from 2006, and everything's going to be normalized to that. So perfect scaling relative to that starting point would follow this line. However, that's not at all what we saw in the last 2 decades. So compared to the 2006 core, Intel's latest high-performance core uses about 12 times as many transistors. This is just, again, a single processor core, not even including the last level cache. And thanks to process improvements, it also is able to run at double the clock rate. But it runs application code only about 8 times faster, or 4 times the performance per clock. So it does 3 times less useful work per transistor per clock cycle. Okay, so now, given that we want to optimize parallel throughput, rather than sequential performance on a single thread of control, are there better ways we could design our hardware? So starting from the big out-of-order CPU core, our first big idea is to go backwards and remove all the stuff we did just to make a single instruction stream go fast. Then we can use what we saved to throw down more independent cores running explicitly parallel streams of instructions instead. But actually, if we think back to our matrix multiply kernel, if we look carefully at this inner loop, we can see that all these iterations are actually independent of each other. So this is one place where we can execute in parallel, running different iterations of the same loop body at the same time. But if we think about that's actually going to look like in the hardware, we have multiple independent cores running the exact same program with only the values of the iteration variable I, or dependent on the iteration variable I changing. So it seems like we should also be able to share most of the control logic, since the different threads are running the same sequence of instructions. Well, this is our second big idea to optimize for throughput. We can amortize the control overhead of a single stream of instructions over multiple parallel executions with, or multiple parallel invocations with SIMD execution. So we go from a simple core with one fetch and decode block, one ALU, and one set of registers, to a core with one fetch and decode block driving several parallel ALUs. We also need separate registers to store the program state for each of the parallel execution pipelines. Now, for each instruction our core decodes, instead of executing the work it describes just once, we can instead process 4 iterations at a time, in this case. Now, it's worth noting that we can do this either with explicit SIMD instructions like Intel AVX or ARM Neon, or via implicit SIMD execution of a logically scalar ISA like you see on most GPUs. But it's the same fundamental idea. And we can scale this idea arbitrarily far. The trade-off is that SIMD execution requires coherent control paths over all the individual executions. So because we're sharing a single stream of instructions, each extra ALU is only useful as long as we have batches of work, at least that big, all doing the same thing every cycle. Now we can deal with divergent control flow, like this branch going 2 different ways on different SIMD lanes. And we can do it by running both code paths one after another, with only those lanes that took the given branch active. So this works, and it allows SIMD execution of arbitrarily divergent code, but any actual divergence comes at a cost of performance, since the diverged SIMD lanes do no useful work in any cycle that the processor is executing other instructions. The last big issue is how we can deal with long latency operations without causing stalls. So from a throughput perspective, stalls can't be efficient because they're wasted time when our silicon's not doing any useful work. So that was a lot of what our big out-of-order processor dedicated resources to. But we saw that it pays a very high cost to do so. But we have lots of independent work to process. And it turns out that we can use that to hide latency as well. So this is our third big idea, that we can interleave the execution of parallel tasks over time on a single core to hide latency. So a given task can still stall, but while we wait for it to become runnable, we can just switch to another task to keep doing useful work. That one can also stall, but as long as we have enough other tasks, we can keep switching to another runnable one, eventually getting back around to the first, once its long latency dependency, like fetching from memory, has actually completed. And the key is that we're actually executing these different tasks on the same physical resources over time to keep them busy. But to quickly switch between tasks, we actually need somewhere to store the state, the registers associated with all the different tasks we want to interleave. So to hide long latencies, we need lots of storage for different thread contexts. So for context, the latency of accessing off-chip DRAM today is up to several hundred cycles. So we potentially need lots of threads to fully hide this. Hyperthreading, like you see in current Intel and AMD cores, keeps only 2 threads active on the processor at once. But in contrast, a current NVIDIA GPU has storage for 64,000 register values per SM, that's what they call a core, or 32 megabytes of register storage over the whole chip. So they spend at least as much on-chip memory on latency hiding as on caches. So in a given amount of memory, there's also a fundamental trade-off between the amount of per-thread state we need to store and the amount of latency that we can hide. So for thread contexts, the number of registers they use are really large. We can only store a few tasks to switch between, so we can't hide very much latency. But if our thread contexts are small, we can store lots of them, letting us hide lots of latency. So this is the fundamental reason why you see things like GPUs get much slower as you use more registers per thread. It's a fundamental trade-off. Now, contrasting all this with the conventional processor approach, you can see pretty much everything here as exploiting abundant parallelism to better optimize for efficiency and therefore throughput. So we can scale up performance with multi-core instead of instruction-level parallelism. We can amortize control overhead with SIMD. And we can hide latency with concurrent threads instead of speculation. So redesigning our processor this way, we've eliminated most of the control overhead. So that lets us spend way less silicon on managing what we want to do and much more on actually doing it, actually executing instructions, fetching, and computing on data. But one thing you'll notice we haven't talked much about is energy. And you probably know that hardware today is limited often by power and energy more than anything. So how should we think about that? So it's useful to orient ourselves by looking at the fundamental costs of different things in hardware. So looking at the memory hierarchy, starting with off-chip DRAM, it takes hundreds of picojoules of energy to load a single 32-bit word of data onto the chip. Once there, it takes an order of a magnitude less, about 50 picojoules, to load it from a large on-chip SRAM, like multi-megabyte cache. It's another order of magnitude less at about 5 picojoules to load it from a small local SRAM of maybe a few kilobytes. And a lot of this just reflects the cost of moving data around the chip, which is tens of picojoules just to go a few millimeters. Finally, actually doing an ALU operation, in this case a 32-bit floating point multiply accumulate, something we used to think about as a pretty heavyweight operation, takes just 1.2 picojoules. Now, this isn't exactly to scale, and in particular, the ALU is actually so small that you couldn't even see it. So let's zoom in more to the logic scale. So here we can see the relative size and energy cost of different fundamental arithmetic operations. So again, our 32-bit FMA was about 1.2 picojoules per operation. By comparison, a 64-bit FMA is 4 times as expensive at 5 picojoules. A 16-bit integer multiply is only 260 femtojoules. And an 8-bit integer add is almost unmeasurable at just 10 femtojoules. So looking at all this, what do we see? Well, one obvious thing, just from that previous slide, is that we can reduce the cost of everything by using lower precision when possible. So going from double precision floats down to 16 or even 8-bit, we reduce the cost of multiplies by 16 to 64x. So we can build way more ALUs to get more performance for the same cost. So it's obvious why reduced precision is such a trend in machine learning. If your app can get away with it, the savings can be huge. But thinking about the relationship between these different costs, we can notice something else. Accessing and moving data totally dominates the cost of computation. So even once we're on chip, to load a single value from cache, it can be 100 times more expensive than to use it in something like a 16-bit multiply accumulate operation. So thinking back to our throughput processor, if the computation is really the work that we want to do, we need to pay attention to the overhead spent not just on control, but also on data movement. Now, obviously, locality is super important, but even if all of our data just moves between the register file and our ALU, we still spend the vast majority of our energy just feeding operands to and from the ALU, not doing actual computation. So here we can see for different common ALU operations, the percentage of energy spent on moving their operands to and from the register file relative to the total cost of performing the operation. So data supply overhead ranges from 3-to-1 for a big 64-bit FMA, all the way to 99% for a 32-bit integer add. So clearly, if we really want to be efficient, we need to find a way to reduce this overhead too. And that's the fourth big idea I want to raise. So again, the answer is going to be to amortize this overhead. And in this case, we can do that by making each instruction do more work. So instead of doing traditional primitive operations like multiply and add as individual instructions, we can instead make instructions that perform complex chains of computation. So what's more efficient than feeding operands to and from a register file? It's feeding them directly from one ALU to the next. So that's a key source of efficiency that ASICs exploit, but we can do that inside our processor too. So for example, it's increasingly common to see specialized instructions for everything from AES encryption to video encoding. Each one of these is what you might call an ASIC in an instruction. It's like a return to CISC. And the quintessential example of this today are matrix multiply instructions. So these are showing up everywhere. And we saw them in both the CPUs and the neural engine in my M2 laptop. So instead of scalar multiply accumulate as the primitive instruction, we have multiply accumulate on an entire matrix blocks as a single instruction. So looking at the example of NVIDIA's tensor cores, the 16-bit version multiplies and accumulates 4x4 matrix blocks for a total of 128 flops within a single instruction. And with this, we get a combined control and data overhead of less than 20%. The int8 version does even more ops and drives the overhead all the way down to 12%. So with these, 80 to 90% of the processor core's energy is spent just doing the fundamental math required by the computation. So that's 10 to 100 times more efficient than primitive instructions. Now, why is matrix multiply in particular so amenable to this approach? The key is that it has really high arithmetic intensity. That's architect jargon for the ratio of the number of operations performed by some function to the amount of data that it consumes. So multiplying a pair of square n by n matrices takes 2n cubed flops, but only requires 3n squared data. So it reuses each input matrix item, like each number in each input matrix, n times. And the bigger the blocks, the bigger the n, the bigger this ratio gets. So matrix multiply is special not just because it's popular in neural nets, but also because its high arithmetic intensity makes it uniquely acceleratable. So there's often a perception, I think, that the details of fast systems are kind of arbitrary, and that what machines are good at is an accident of history. This idea sometimes gets called the hardware lottery. But the fundamental physics of hardware make computation cheap and data movement expensive. So I think this is no accident. Really, all highly acceleratable computations need high arithmetic intensity, or else you never spend much of your effort on actual computation. Now that doesn't mean there aren't useful things that don't fit this mold. Like sorting is still going to be a really useful operation. We just shouldn't expect fast sorting instructions to be the key to future hardware. Now, the same is true of all the ideas that we developed for our throughput processor. So why did we move to multi-core? It was because of fundamentally diminishing returns from finding parallelism within a single instruction stream. We have SIMD because adding more ALUs is basically free relative to the cost of controlling them. With abundant parallelism, we can hide latency more efficiently than with speculation. Reducing precision rapidly cuts down the hardware cost of computation. Complex instructions amortize the huge cost of data movement. And arithmetic intensity is essential to any computation we have hope of accelerating. Each idea here reflects fundamental trade-offs and opportunities, which is why we see them recur in most high-performance hardware today. But again, the challenge is that effectively exploiting this hardware requires changing how we program. But if we do, we'll be rewarded. So we saw earlier that adapting our code based on these ideas, we can reach tens of teraflops on my laptop or a petaflop on an H100. So 100 to 10,000 times faster than even optimized C crunching 32-bit floats on the fastest single CPU core today. All right. So now I want to return to the claim I made at the start, that to unlock the potential of future hardware, we need to rethink our programming systems. So what do these fundamental forces and the trends they're driving in hardware mean for how we should program the processors of tomorrow? And in particular here, what do they mean for the tools that we in the programming systems community should be trying to build? So I want to talk about a few ideas. First, one thing we saw is that data is essential to performance. So to be fast, programming languages need to move from composing complex data structures out of simple scalar primitives to richer collection-oriented models. So this is really the key power of most high-performance DSLs. We call them domain-specific, but I often find it more useful to think of them actually as data structure-specific. So for example, databases can radically optimize SQL queries, not so much because of something in the domain of credit card transaction processing, but because the relational model is expressive enough to allow simple, highly analyzable programs like this, while admitting what Cod called physical independence, admitting a huge space of possible implementations for a given program. And control over the fundamental data structure at the aggregate or collection level gives SQL implementations huge leverage to optimize queries in different ways. And similarly, in some of my own work, I think Halide is less specific to the domain of image processing than to the data and communication structures of multidimensional arrays and stencils. We found we could accelerate simulation and other graphics apps by adapting a Halide-like model to hierarchical sparse grids in the Tai Chi language. And with Simit, we built abstractions for both graphs and sparse matrices, and a programming model that exposed connections between these to the compiler. So getting the data abstraction right simultaneously enables simpler, more declarative programs and more powerful compiler optimization. And this is the real leverage and lesson of DSLs. Now, another key lesson we learned about hardware was that getting performance increasingly requires exploiting complex instructions. We can't just keep pretending that our computers just do simple primitive arithmetic. So first, today, I think if you're not designing your language and compiler to exploit SIMD execution, you're giving up most potential for performance and efficiency from the start. But beyond simple vectorization, how can we hope to target the increasingly complex and diverse specialized instructions that I said are starting to really come? So one approach is turning instruction selection into a program synthesis problem. So this can automatically target really complex instructions in modern hardware, but the problem is that it's orders of magnitude slower than a normal compiler. In contrast, my former student AJ Root just presented a more practical alternative at ASPLOS this year in a new code generator for Halide called Pitchfork. So here, by carefully designing a backend IR to model the algebraic structure of accelerated operations in a specific domain, in this case, fixed point digital signal processing, and then using synthesis offline rather than in the compiler to drive the creation of rewrite rules, we're able to generate code with performance close to expensive synthesis, but with compile times like a normal compiler on the order of seconds. Another key issue is how to get compiler engineers off the critical path to figuring out how to target each new complex instruction at all. And to address this, we've been developing the idea of what we call exocompilation. So it's a language design approach that turns the compiler inside out and lets programmers directly control and extend its functionality from safe user-level code. So in our language EXO, specialized instructions aren't special. So they're just regular functions that describe the effect of an instruction that's then annotated with the backend code that it corresponds to. So you can think of this basically like assembly intrinsics, but extensible by the user. So the function definition provides the compiler with the semantics for the instruction, and it can use that to both pattern match for where to generate it and check the safety of substituting complex code. Next, I want to touch on the roles of automation, safety, and control in programming languages. So as language designers, we make programmers more productive by designing ways to abstract away details of things like memory management. And in the process, we get to save them from countless bugs. And as compiler engineers, we love to automate performance optimization. So automation is great when it works, and for most people, most of the time, it's what they want. It's what they should want. But there's a neglected dark side of programming that I like to call performance engineering. So performance engineering is where expert programmers optimize programs to levels that compiler automation alone can't currently reach. And this is what drives the performance of everything from machine learning to image processing, games, graphics, and HPC in practice. And for performance engineers, writing high-performance code requires control. The problem is that with traditional programming languages, taking control requires completely giving up safety. So they have to live entirely on the dark side, where there's foot guns hiding everywhere, where something like CUDA is considered a high-level language. But I think we can do better. If we want high-performance programming to be productive, we need programming systems that provide both safety and control. So this was a big idea that drove us to make Halide. Combining high-level specifications of the computation to be performed with a language of scheduling operators to safely and concisely control how they're mapped to the hardware. And critically, the language here is designed to guarantee that changing the schedule can never change the result, or the result that we compute or cause memory bugs. So we think about how this system is, the model this is providing to programmers. This now allows performance engineers to cognitively offload the problem of correctness to a compiler writer, just as the compiler writer offloads responsibility for performance optimization back to the performance engineer. So this idea has grown into what we like to call user schedulable languages. So our group and others have built lots of recent systems on this idea. And with EXO, for example, we're taking this in new directions with even lower level control and user-defined extensibility and automation. But the promise in all this work is to improve the productivity of performance engineering by providing power users with safe control so they can optimize faster without fear of breaking the program. And this is not an area that we spend lots of time focusing on when thinking about language and compiler design, but I think we should, because performance engineers are a really small but very high leverage niche. So from our own work, I think there are maybe hundreds of serious Halide and Tai-Chi programmers in the world, and certainly fewer than 20 EXO programmers. But they ship foundational code for applications and systems used by billions of people. So there's probably Halide code running on most of the devices in this room, and EXO and Tai-Chi code now on many more. And we've even started to see how to put these safety guarantees on stronger foundations with verified scheduling language and compiler and Coq. And you should go see my student Amanda's talk later to learn more. Another major opportunity is in the design of hardware itself. The hardware design today is fundamentally a programming problem, just with hardware-oriented languages, compilers, and cost models. And this is also a case where traditional tools have chosen to sacrifice safety in the interest of low-level control. But again, I think we can do better. So Arvind, who sadly we just lost last week, was at the forefront of bringing programming language tools to hardware design. So his language, BlueSpec, brought a statically safe model of composition to hardware, enabling true modularity for the first time. With Adam Chapala's group, they adapted this idea to an embedded hardware design language in Coq, providing end-to-end verified hardware. And recently, Rachit Nigam has combined safe composition with even greater cycle-level control of pipelining through an RTL-level type system. So there's so much opportunity for this community to make hardware design better. In my own work, we found the idea of externalizing scheduling for safe and productive control is also appealing for hardware design. So in collaboration with Mark Horowitz's group, we adapted a version of Halide to directly generate hardware and use schedules to map the space of design choices. Now finally, I want to point out that I think broadening our notions of correctness and program equivalence can unlock opportunities for performance over and above everything else that we've talked about. So we saw earlier how reduced precision was a key part of the biggest acceleration opportunities. And you shouldn't just write this off as crazy machine learning people yelling YOLO. Like, lots of numerical problems have no discrete definition of correctness. For example, low-level image processing operations, like the demosaicing in any camera, are usually ill-posed problems with no one right answer. Instead, there are what we might think of as varying degrees of correctness, higher or lower quality that a given implementation can achieve on a given input. So for problems like these, it turns out that gradient-based optimization is a really powerful tool to maximize the quality of a given implementation by automatically optimizing its parameters. But it's not just something for neural nets. By developing new differentiable programming techniques in languages like Halide and Tai Chi, we found that you can quickly adapt classical algorithms, learn more optimal parameters, and get deep learning level performance with orders of magnitude less compute and memory. And I think this points towards a whole new way to bring learning into performance optimization, especially for performance critical tasks like real-time imaging and video. So we started to investigate learning to solve these tasks by combining program synthesis over this broad space of differentiable programs with gradient-based optimization of those programs' parameters. So we can automatically synthesize, train, and generate optimized code for whole families of solutions that differently trade off performance and quality. So here I'm showing some of our latest results applying this to demosaicing and super resolution, led by my student Karima Ma. So in the graph on the right, higher quality is up and faster is to the right. And this is a log-log scale. So our automatically synthesized new algorithms, which are the uppermost red curve, are at least an order of magnitude faster, higher quality, or both than either traditional or deep learning methods that came before. But critically, there's no one best solution. Instead, there's a whole Pareto frontier of implementations that each provide a different optimal balance of performance and quality. So these are all functionally equivalent and correct programs in some sense, but they compute completely different numerical results with completely different code. All right. So these are a few ideas that I found fruitful when designing new programming systems for high performance in this world of modern hardware. And now I want to just conclude by saying that the trends making hardware harder to exploit with old ways of programming, these are fundamental and here to stay. But more than a problem, I think it's a huge opportunity for this community. We can be the ones to unlock their potential for enormous computational power by fundamentally rethinking how we program. And finally, I want to quickly acknowledge the many students and collaborators that I've been lucky to work with over the years. So here I'm highlighting current students and people directly involved in work that I mentioned. And I especially want to thank Gilbert Bernstein, who was critical in helping me find a hopefully coherent story in a jumble of ideas, and Kayvon again, whose lectures on GPUs were the basis for some key parts of this. All right. With that, thanks.
So there's an audience mic here in the center. If you've got questions for Jonathan, we've got about 10 minutes.
Thank you for a great talk. So I wonder your opinion about the software hardware co-design approaches, because you are talking about programming languages or systems and also hardware. So maybe collaborating between software and hardware designers can even unlock better potential. So what do you think about that?
Yeah, absolutely. So obviously, I think there's huge potential in we've seen by changing hardware. You can actually think of the whole throughput processor argument as a bit of a software hardware co-design process, where we're saying if we're willing to change the programming model to what I was building towards was you could think of it as being something like a GPU, but although the same ideas appear elsewhere. If we're willing to change the programming model to OpenGL shaders or CUDA, how could we make the hardware much more efficient, and vice versa? How should we change the programming model given ways we know we can do computation faster? But I think the same idea can be carried much further in different settings. In my own experience, I've worked on projects where we've designed hardware architectures like the Gemini matrix multiply unit from the RISC-V ecosystem that we built at Berkeley. That's actually literally where the EXO programming language came from originally. We basically found that to be able to build a high-performance kernel library for this new piece of hardware, we needed a new programming language to make the process easier. So I think absolutely hardware and software design happening together is the way of the future.
As it turns out, this question is sort of an extension of the previous one. It seems like a logical extension of the throughput-oriented processor argument is that everything is gradually becoming an FPGA. It's sort of because FPGAs are very throughput-oriented, and you're in HDLs, you're very frequently talking about time enclosure and ensuring memory locality and all of the things you're talking about. What lessons do you think that we can learn from the HDL community and their successes and failures?
Great question. So actually, there's a whole section of this talk that I cut for time where I brought up this exact issue. So I think a really common idea that comes back every decade or two and has come back more recently because of these energy arguments is that hardware is fundamentally spatial. These hardware costs with data movement dominating everything are fundamentally spatial. So maybe we should throw out the idea of processors entirely and make architectures and programming models that directly map onto that underlying spatial substrate. And I actually think this is a bit of a, I'm not the only one who thinks this, but it's definitely not the only opinion in the world. There are people who strongly believe in spatial architectures. Things like CGRAs and reconfigurable data flow architectures are an even more popular way of doing this today. I actually think it's not necessary, and maybe not even a good idea. And the reason, at least to replace most of the sorts of things I was talking about, and the reason is several parts. So one, it's not the case that traditional software programming models are not spatial. So things like parallelism, data parallelism, locality in how we use memory, putting data in different memory spaces like explicit scratch pads, which we often have to do writing these kinds of programs. All of those ideas also embody spatial structure, expose spatial structure to the hardware, and that's why they're efficient. We could take this more offline, but I think combining all the ideas we saw, by the time you reach the point where you're spending 80% of your energy doing useful work in the ALUs, there's no reason to make your life any harder by adopting a non-processor-like programming model. And the last thing you tend to see is when you want to program an FPGA or a CGRA to do something complicated, you wind up building a state machine to run different stuff over time, which is basically a processor, but you're building it in reconfigurable, like you're building it at the software level and having to reinvent all of computer architecture while you do it. So I actually think this sort of processor-style model, but with all of these throughput ideas brought together and potentially much coarser-grained operations on the inside is the most likely way forward.
Thank you.
Hi. Thank you for the very insightful talk. A few decades ago, there was this architecture, VLIU, in which you had multiple integer pipelines that were fully exposed to the developer, to the compiler, and it was up to the compiler to emit this huge instruction to keep everything busy. it lost to out of order at the time, and it's a thing of the past. Are we slowly going back to something like that?
So first of all, VLIW didn't lose. It's actually very commonly used in embedded and high performance settings. So last I knew, Google TPUs, for example, internally are VLIW machines. Various GPU-like things people built are VLIW machines. The idea there basically is saying, I want to remove the control overhead even more by pushing it all onto software. I think the fundamental challenge with that is actually that there's just limit, as programming systems people, we know there's stuff you can do statically, and there's stuff that you can only reasonably do, or you can do a much better job with dynamic information. And VLIW fundamentally punts all of the instruction scheduling to a static one-time offline process, and out-of-order processors and other techniques have dynamic information at runtime, so it can do a better job. It's not just that they're easier to program. But there are other ways, similar ways of amortizing control overhead, like with vectorization, and with those I actually don't think we find that with a bit of, it's hard to make C just magically use vector instructions well, but I've had a lot of experience building other languages with vectorization and data parallelism in mind from the beginning, and in those contexts, it certainly doesn't seem that we're hitting the same kind of brick wall of diminishing returns.
Thank you.
Thanks.
Hi, thanks for the great talk. You talk about this kind of idea of we want to provide safety and control to our performance engineers, which I really like, but this seems like a really hard problem, especially sometimes optimizations we may want to perform we know are correct, but only because we know stuff about the data we're using. And inherently this seems really related to a lot of very hard and even undecidable problems. Yep. And I'm wondering, do you think there are kind of limitations then on when we can provide, when we need to maybe say, either we let people do something that we can't prove is safe, or we don't let them do it? Kind of, how do you make choices there? And kind of, how do we provide the control people still want if we can't prove safety?
Yeah, great question. So I think there's definitely a spectrum of how much safety you provide to people. I think the big overarching, we don't necessarily need, Adam's right behind you may disagree with this, we don't necessarily, at least on day one, need to formally prove everything in very deep ways all the time. It can be really useful even just to have automated tests to quickly verify that your programs are equivalent as you optimize them. But there are still a lot of contexts where by being careful in how we craft the abstractions that we program with, we can kind of carefully shape the interface to make analysis problems key to reasoning about different safety choices tractable. So in the case of the EXO language, for example, it roughly is at the semantic level of something like C because you're controlling things at that level, but currently it's limited everywhere to only use affine indexing and static control, something roughly equivalent to the polyhedral model, because it makes all of the dependence analysis questions decidable. I certainly think my experience building practical programming languages is that escape hatches are really useful. You still need them no matter what. But you also want to design the language so that you bound the blast radius if things go wrong.
Cool, thanks.
So you had a nice slide about storage hierarchies and the power costs of moving between different levels. I was thinking of that in terms of there being basically straight line distances and it's expensive to move across distances. But there's another dimension, which is cache coherence protocols and fancy concurrency control. How does that fit into this kind of model? Is it already incorporated in the different suggestions that you made?
That's a good question. So I don't think cache coherence protocol overheads are included in, these are like the data I've taken from Bill Daly's work over the years. This is raw costs of accessing SRAMs of different sizes and going over a DRAM bus. So it's not including additional data movement from the communication and state management logic to deal with complicated cache coherence protocols. So those would add overhead on top of all of this. I think there's, I think there's always going to be trade-offs where kind of depending on how restricted our programmers are going to be, how restricted our programming model can be in a given context, We can probably get wins by stripping those things away, but there are often usually still ways to get most of the benefits with relatively modest overheads and make programming a lot easier for many more settings. So I think we'll continue to see a spectrum between relatively general purpose things that still do throughput optimization, but pay some overhead for ease of programmability, and much more extremely optimized things that are much more stripped to the bone.
I greatly enjoyed your slides and
Thank
your
you.
explanations. Thank you. My question is, can programming be liberated from the von Neumann bottleneck? And is your talk essentially an up-to-date and hardware-focused version of Bacchus's message?
To some degree, yes. But related to the question earlier about changing our programming models to think about, everybody basically becoming a hardware designer and all starting to program FPGAs or things like that. I actually think, I criticized the sequential model of processors as not being the only thing that by itself can give us any reasonable performance anymore. But the flip side is that I think it's actually a brilliant model we've seen over decades in that it's the only thing we've seen that actually does enable us to build abstractions that people can understand, compose complicated systems together, have sane stories for debugging, have compile problems that aren't, if we going into the spatial world, compilation suddenly starts taking days and requiring solving NP-hard optimization problems. So I think there's a lot to be said for trying to hold on to the idea of processors, but at the same time, alleviating their weaknesses by expanding in these various directions, adding parallelism around and inside them, expanding what a given instruction means, and shifting the constant factors in all those sorts of ways.
Thank you.
Thanks for the question.
And with that, let's thank Jonathan.
Thank you.
So we now have a about 30-minute break. I would ask that people mostly come out of this room because they need to do some reconfiguration for the sessions later this morning.